So as is traditional in these contexts, of course, I would like to thank the organizers for having invited me to come and speak to you, to give a talk here. And as one of the oldest women here, I feel I'd like to respond to what Matt said at the very beginning of the week, which has been a wonderful week so far, actually. I hope it will continue for the next hour. So Matt said something about how in 1991, when there was a conference in Oaxtepec, there were no women speakers, there were no women who wrote articles for the conference proceedings. And I'd like to point out that at that time, Brooke, Brenda, Ulrika, and I were probably the oldest women in outbreak topology, which may explain why there were, oh, sorry, and Kathryn, sorry. Other Kathryn as well. So there were very few of us, and we were all very young. We were postdocs or PhD students. So it's really wonderful to see the change that has happened over the last 25 or 26 years. I look in this audience, and I see so many young women. It's just fantastic. I'm really happy about that. And Paul, so I'm going to make a very oblique reference to Paul, has contributed to that as well by being a wonderful mentor for young women in algebraic topology, and I really appreciate that. I'd also like to say something about the genesis of this project. This is a project that sort of spans 3 generations, since Bill, Ben, and I are all involved. So this started as a question that Bill and I had in some work we were doing on embedding spaces that we thought, well, this should be true, but we thought we needed to use a factorization homology to prove it and didn't feel competent to do so. And then a couple of years ago, when I was at Talbot, Ben came up to me and said, is that problem still open? Because he'd heard Bill talk about it. And I said, yes, because we felt like we couldn't really come up with a solid proof. And he said, well, can I work with you on it? I said, fantastic. Well, in the end, it turned out that we don't actually need the full power of factorization homology, that we can use sort of baby factorization homology to answer this question. But it's been a wonderful collaboration, and I'm happy to tell you about it today. So first, I'd like to start by recalling some things about configuration spaces. It's early in the morning. Let's get started slowly. Let's get warmed up. And explain something about why we might be interested in them, what is known about configuration spaces of products, and then explain how we're going to attack this, or how we attack this problem using machinery of operads. So first of all, let's recall a few things about configuration spaces. So mostly to introduce notation. I presume everybody's actually heard of these things. So our X is going to be a topological space. Then from that topological space, I'm going to define the configuration space of k ordered points in X. So that's the set of k tuples, x1 up to xk, which are all distinct, so that if I is different from j, then xi is different from xj. So this is the configuration space of k ordered points in X, where we use the subspace topology coming from the product topology on X. You see, I teach point set topology, so one gets in the habit of telling these things. So this admits a sigma k action, obviously, by permuting all the points. And this sigma k action plays an important role. And if you quotient out by the sigma k action, then you get the space of unordered configurations, which is also very interesting and important. So why should one care about configuration spaces? Well, they pop up all over the place in mathematics, in particular in algebraic topology. So we know, for example, that the fundamental group of the configuration space of k points in R2 is the pure braid group. If we look at the unordered configurations and take the fundamental group of that, then it's the actual braid group on k strands. If we look at the configuration space of k points in the complex plane and we mod out by the sigma k action, then what we get is a space of monic polynomials with complex coefficients with k distinct roots. And this is an interesting way to study that space as well in terms of configurations. It's easy to do some elementary computations for these configuration spaces, see what their homotopy type looks like. If we look at the configurations of 2 points in Rn plus 1, then we have the homotopy type of Sn. Just like the configuration space of 2 points in the n spheres also have the homotopy type of Sn. Now, in terms of things that are already known about this, so there's work of Cohen, Fred Cohen in this case, telling us about the cohomology of the cohomology algebra of the configuration space of points in the Euclidean space. So that's just what I want to say. That he gave an explicit presentation of the cohomology algebra of the configuration space of k points in Rn with integral coefficients. It's a beautiful presentation that has been very widely used. And then there's work of Peter May, and perhaps others, in which instead of looking at one configuration space at a time, he took a more global approach and looked at all of the configuration spaces simultaneously, and looked at what you get when you take, just a second, I want to make sure I get this right. If you take the disjoint union of these configuration spaces, or sorry, I'm going to have to copy this. Right. That we can, sorry, I'll just write it like this, that we can build a model for loops n, suspension n of a space X from all of the configuration spaces of Rn, k greater than or equal to 1, and the iterated Cartesian products of these spaces. So by looking at all of these spaces together, we can actually learn something about these iterated loop, iterated suspension spaces. So now, the meta question that I want to ask today is the following. If I'm given some sort of decomposition of this space X, I mean, this is the sort of thing we like as topologists, right? To have a space that we know that's broken up into smaller pieces that we know how to handle. And we'd like to be able to say, if I have a decomposition of a space X, is there an induced decomposition of the space of configurations? So if you attended Ben Knudsen's talk yesterday, he was talking about, well, what if you have a CW complex and you look at configurations in a CW complex? What can you do some sort of CW structure there? I'm going to ask similar kinds of questions today. So the meta question is, if I'm given some sort of decomposition of a space X, does it give rise to a decomposition of the space configuration space? That's the sort of question I want to answer today. So let's do an easy example. If we look at a disjoint union of two topological spaces, and we look at the configurations of k points in a disjoint union, well, it's going to be made up of I points in one and k minus I points in the other in all the ways possible. So if I look at the configurations of k points in the disjoint union of x and y, then I know that that breaks up as disjoint union I plus j equals k of configurations of I points in x, configurations of j points in y, and then we just have to make sure we get the actions right. So cross it up over sigma k, where we're embedding sigma I cross sigma j and sigma k as a subgroup in the obvious way. So this is really clear that if I have a decomposition, if I have a disjoint union, I take I points here, j points here with I plus j equals k, and it gives me a configuration of k points in the disjoint union. But now you can say, it's obvious, we always, once we have a problem answered in one side, we'd like to look at the Ekman-Hilton dual of it. So we say dually, what can we say about the configuration of k points in x cross y? What can we say in that case? Well, this is a lot harder. The problem with this is that we can find ourselves in the following situation. So again, taking a page from teaching point set topology to undergraduates, let's suppose that this is our space X and this is our space Y, and we're looking at X cross Y. We can look at a configuration of points in X cross Y, and it could look something like this, where we have a bunch of points with the same X coordinate and a bunch of points with the same Y coordinate. And so projecting onto either X or Y is not going to give us a nice configuration. So how do we break up a configuration like this into configurations in X and configurations in Y? Well, the point is we're going to have to work up to homotopy in order to do it, but that's what we're going to try to do. So the goal today is to provide a formula for configurations of k points in X cross Y in terms of configurations of I points in X for some I and configurations of j points in Y under certain conditions on X cross Y, which is going to enable us to sort of homotopically separate out these sorts of situations that are complicated. So let me talk about some earlier work along these lines. First of all, building on Cohen's presentation of the cohomology algebra of configurations in Euclidean space, he worked together with Larry Taylor to prove the following result in 1978. So what did they do? They looked in particular at the cohomology algebra of a configuration space of a product where you have a manifold M together with the Euclidean space. So here, let's let M be a smooth manifold without boundary. Of dimension M. And I'm going to, what they provided was a formula for the cohomology algebra with coefficients in a field of the configurations of k points in M cross Rn, coefficients in a field k. And they said as an algebra, that's isomorphic to the following. We take the cohomology algebra of M to the k, tensored with the cohomology algebra, so I'm dropping the coefficients here. There we go. Tensored with the cohomology algebra of configuration of k points in Rm plus n, so you're shifted by the dimension of the manifold, again with coefficients in k, quotiented out by some ideal j, where j is an ideal of which a presentation is given explicitly in terms of the presentation of the cohomology algebra of the configuration space. That, okay, and here I should probably say n greater than or equal to 2. So j has an explicit presentation which is given in terms of the cohomology of M and Cohen's presentation that I gave before of the cohomology algebra of the configuration space in Euclidean space. So that was one result that was known. And we're not really going to go in that direction. We're going to go more in a direction inspired by work of Dunn and Brinkmeyer. So Dunn, back in, I believe it was 1988, yes, and Brinkmeyer in 2000, sort of completed the story. So what they did was the following. They were looking at configurations in the cube. So let's let, I'm going to write box n for the n-fold product of the closed interval from 0 to 1. Okay, so I have n copies there. And what they were looking at was configurations in the cube like that. And what they were able to do was to provide a formula, so for any kmn greater than or equal to 1, they provided a formula for, or a description of the homotopy type. Let's see that, a description of the homotopy type of the space of configurations of k points in the m plus n cube in terms of configurations of I points in the M cube and j points in the n cube, where here I and j were between 1 and k. So they provided this explicit description. Now, I want to say a few things about this description. This formula is complex. So it's fairly complex because it's given in terms of what's called the Boardman-Fock tensor product of operads, which is something I'm going to remind you of in just a moment. In terms of the Boardman-Fock tensor product of operads. I mean, it's still manageable. It's like if you feel comfortable with the Boardman-Fock tensor product, it's actually not that complicated, but one needs to take time to get a little comfortable with this tensor product. But I'm going to explain it to you, and I hope you'll be somewhat comfortable with it by the end of the hour. So one remark is that when you're talking about cubes, you have a nice rigid rectilinear structure that's coming into play. And this particular rectilinear structure plays an important role when you're trying to sort out this homotopy type. This makes it much, much easier to understand these configurations. So we need to look for something that's kind of analogous to working with this sort of rectilinear structure. Another remark is that here, again, it was clear, just as in this situation and in the work of May, that it's important to work with these configuration spaces sort of globally, not one K at a time, but a lot of configuration spaces all at once. So let me give a more refined description of today's goal. And explain more precisely what it is that we're going to do. So we're going to find a formula for the homotopy type of the configurations of k points in a product of two manifolds. Now, these will be smooth manifolds without boundary, and they will be also framed. That will play the role of the rectilinear structure we have here. So where M and N are smooth, framed manifolds without boundary. In terms of configurations of I points in M and J points in N. So we're going to try to do something analogous to what Dunn and Brinkmeyer did. But we don't have quite the rigid structure that they had when they're working with cubes. So we have to be a little more careful. So in order to do so, when I say in terms of, it's going to involve this Boardman-Fock tensor product, I need to introduce some operatic machinery. So let me just either tell you or remind you of what we need to know about operads in this context. So now I'm going to switch to a context where I can be working in any symmetric monoidal category. So V closed symmetric monoidal. So I'm going to have an internal Hom. And because this is a homotopy theory conference, I'll call the unit element object S, even though I'm usually working with spaces rather than spectra in this context. So this is going to be a closed symmetric monoidal category that is also going to be co-complete. So I'll have all the co-limits I want. I really need only, I think I really only need co-products most of the time, but anyway, we'll just say that we have all co-limits. And from that, I can start to build up the framework of operads in this category. So if you want to, you can just be thinking about V being spaces or simplicial sets or spectra, whatever your favorite category is. So from that point, we can define what we call symmetric sequences in V. So what are the objects here? So these are symmetric sequences. So I'll use this notation as sort of a calligraphic letters for the symmetric sequences. So these are sequences of objects in V, one for each natural number, and where xn admits an action of this symmetric group for every n. And the morphisms are what they have to be, sequences of morphisms that are equivariant with respect to these actions. And one thing I want to mention is that there are two monoidal structures on here that are important for what I want to tell you now. So there's one which is called the graded tensor product, which I'll denote circle dot. And if I have two symmetric sequences x and y, x circle dot y in, oh, I should say that this is called arity n, or level n. X circle dot y in arity n is nothing but the disjoint union of the sum over L plus m equals n, x in arity L, tensor y in arity m, and then you're going to tensor up with sigma n over sigma L cross sigma m, embedding it the same way, where you can think of sigma n as an element of this category V by taking a disjoint union of copies of the unit element S over the elements of sigma n and defining a permutation action on that. So anyway, we can have this. This gives us a symmetric monoidal structure on the category of symmetric sequences. And there's also a non-symmetric monoidal structure, which is usually written in circle, composition, for reasons that will become clear in a moment if you don't already know them. So this is given by disjoint union for all k. You take x in arity k, tensor over sigma k with the kth iterated graded product of y in arity n. So this thing is highly non-symmetric and is what's going to give us operads. OK, so now that we've defined those monoidal products, I can remind you of what operads are in a very compact way and introduce the operad that will be, or the type of operad that will be the most important for our discussion today. So then we move on to the category of operads. And these are simple one-color operads, not infinity operads. Just put your hand, really easy operads. So these are going to be monoids in this category of symmetric sequences, considered with respect to this non-symmetric monoidal structure, the composition structure. So this sort of thing we'll have will be a symmetric sequence P together with a morphism of symmetric sequences from the composition product to P. So if you'd like, you can think of elements in Pn as trees with n leaves. And when you're doing this sort of composition, what you're doing is feeding into each one of those leaves something that's coming from P. So we have these sort of monoidal structures. This will be a multiplication, and there's a unit as well with respect to the unit symmetric sequence. And I want to give you what is going to be an important type of example in this context, which is going to be an endomorphism operad. So if I fix an object in V, I can define an operad n to V. And what is it in arity n? I'm going to use my internal Hom in the category V from V tensor n to V. And then the multiplication is given by actual composition. Well, sort of the category theoretic analog of this composition, which is to say that if I'm looking at, say I have an F, Hom V tensor K to V, and I have GI, which is Hom V tensor Ni to V, 1 less than or equal to I less than or equal to K, then this gives me, I can look at the composite here of F composed with G1 tensor GK, and this is in Hom V tensor N to V, where N is the sum of the Ni's. So this is a very canonical family of operads, and it's the one in which we can express the important property of operads. Why do we care about operads? Because operads encode algebra structures, n-array operations, and relations among n-array operations on objects in the category V. So the way we can talk about that is to say that when we're looking at algebras over a particular operad, so what we can say is that operads encode different types of algebra structures on objects of V. That is to say, we can talk about a P algebra. It's going to be an object V together with an operad map from P into the endomorphism operad of V. So a morphism of symmetric sequences that respects the multiplicative structure. So in particular, we're going to get a map for all n from Pn V tensor n to V by taking the adjoint of what you get in array n here. And what you see is that Pn parameterizes n-array operations on this algebra V. So that's what it's there for. And you can think of this, I like to think of this as some sort of representation of the operad P on the object V. Generalization of representation theory. OK. The next step is one that sometimes causes a bit of trouble when people are encountering it for the first time. It's the notion of modules over operads. But this is crucial for what we want to talk about today. I have to do it. So I'm going to think about the category of right modules over an operad P. So this is going to be right modules over P. That is to say, it's going to consist of a symmetric sequence together with an action map of P on the symmetric sequence. So we're going to have X, which is a symmetric sequence, together with an action map, which would be a morphism of symmetric sequences from X circle P to X, satisfying appropriate associativity and unit conditions. So associativity and unitality conditions. OK, so that's what we mean by a right module over an operad. And one thing I want to point out is that we can have a category that I'll write mod of V, which is going to consist of all modules over all operads. That is to say, the objects in this category are pairs of an operad P and a right P module X. And then there's a natural functor from mod V to op V that just forgets the module. Okay? And at some point, we're going to be interested in thinking about sections of this particular functor. So I need to give you what is the most important example of modules over operads. So what we're going to do is take an obvious module over the endomorphism operad. So now we're going to fix two objects in the category V and look at sort of a hung module over this endomorphism operad. So example, if I fix V and W, I can define a module that I'll call HOM VW that's going to be a right module over the endomorphism operad of V. And how is it going to be defined? Well, I have to tell you what's in arity n. And Hom VW in arity n, I use the internal Hom of my category again from V tensor n now to W instead of to V. And if you think about it, this sort of composition will now give you a right action of the endomorphism operad on this symmetric sequence. So the right action Hom VW tensor, sorry, not tensor, circle, and V to Hom VW is given again by composition. So this gives us a whole family of sort of canonical modules over this canonical operad. Another example that works for any operad is that, of course, just as any ring is a module over itself, any operad is a module over itself. So we know that P is going to be a right P module, where the right action is given just by the multiplication of the operad for every P that's an operad. So in particular, what this tells us is that this functor pi that I was talking about on the board over there actually does admit a very natural section. Let's call it iota from up V to mod V that's taking the operad to the pair P, B. OK? So we can always do that. All right, so symmetric sequences, operads, modules. Where are we going next? Oh, I want to say something about, a little bit more about modules first. One remark is that this category of modules can also be, or is equivalent to, a very nice pre-sheaf category. Pre-sheaves in V. And this is a very useful way to describe this category, particularly when you're interested in actually doing homotopy theory. So remarks. First of all, that mod P, as I described it, as I defined it, is equivalent to a nice pre-sheaf category, whose description I won't give you today, but if you're used to thinking about this sort of thing, you'll realize immediately what it has to be. But this is a really nice way of describing it. And the second one is that if I have a morphism of operads, then it's going to induce an adjunction on the categories of the module categories. You can push forward the structure from P modules to Q modules, or pull it back. And it's going to be useful for us to be able to push module structures forward and back in the usual way. This functor is really just tensoring over P with Q, just as it would be in the case of ordinary rings and ordinary modules. OK, so the tool we need in order to carry out our program of describing configurations in a product in terms of configurations and the factors is the Boardman-Fock tensor product of operads and a lift of that to the category of modules. So I need to spend a moment talking about the Boardman-Fock tensor product. So Boardman-Fock tensor product was, of course, introduced by Boardman and Fock, unsurprisingly, around 1973. And the reason they did it was to be able to characterize, to describe those operads that tell you when you have two compatible algebra structures on an object. So now we're going to restrict the V's that we're considering. We're going to think only about V being either topological spaces or simplicial sets. I think it probably works for any Cartesian monoidal category, but I haven't actually checked. So let's take V to be topological spaces or simplicial sets. Now in this context, so what they showed was that there exists a bifunctor, which we'll just write tensor, from operads cross operads to operads that has the following property. So such that P tensor Q algebras, where P and Q are now two operads, are either P algebras in the category of Q algebras, or Q algebras in the category of P algebras. So there are objects in V with compatible commuting P and Q algebra structures. Okay, so they gave an explicit description of this. And the idea is the following. You can construct it as follows. You can take the coproduct of P and Q as operads. And if you've ever thought about what the coproduct of, for example, associative algebras is, and realize how complicated that is, imagine taking a coproduct of operads. It's extremely complicated. I mean, very big. Not so complicated. Easy to describe it. It's just huge. And then you're going to quotient by something. You're going to quotient by something that's going to commute P actions and Q actions. So where, now I don't have colored chalk, so we'll do our best here. If I have, suppose I have something in P. Ah, wonderful. It's hard to give a lecture about operads without colors. OK, thank you. Well, anyway, P will be white. So this is something in P3. And Q, I'll take the same Q and feed it to P at all of these. Q, Q, Q. So Q is in Q2. This is going to be equivalent to, well, I can pull the Q through P. And notice it's exactly the same Q every time. So I take Q and pull P through. So here's P. And what you see is that in both cases, I have an operation of arity 6, the total number of leaves. And here there has to be some permutation tau that has to act on it, because you're permuting actually the entries. But you allow yourself to pull Q through P in this manner. And this turns out to define exactly what you need in order to have this operad that characterizes P algebras in the category of Q algebras, and so on. OK, one remark is that everybody has, you've all done at least one computation like this without knowing it. So example, let's let us be the associative operad, so the operad that characterizes associative algebras. And if you take strictly associative, not A infinity, if you take the tensor product of these, what does that mean? You're looking for algebras with two compatible associative algebra structures. Right? So you have an object that has two compatible associative algebra structures that commute with each other. Then we know actually there's only one, and it's commutative. So it's actually equal to the commutative operad. So this is the, I guess it's Exman-Hilton trick. So things can go wild, can change wildly when you do this sort of computation. OK, so in earlier work, Bill and I proved the following. We wanted to lift this Boardman-Fock tensor product of operads to modules. Okay? And what we showed was that if we consider the Boardman-Fock tensor product of operads, we know that sitting over that, as I explained earlier, is this category of all modules over all operads. And we have this projection down here, and here we have modules over all modules over all operads again. And what we showed was that you can complete this picture. You can lift the Boardman-Fock tensor product here. Let's call it tensor tilde, in such a way that it also commutes with respect to this section. So what do we know about this? Let me just explain what this picture is trying to tell us. If I have x, which is a P module, and y, which is a Q module, then their lifted tensor product is a P tensor Q module. Okay? That's what it means that this diagram commutes with respect to the pi's. And the fact that it commutes with respect to the iotas means that we know exactly how to define this tensor product, at least on free modules. So that's one thing. So it turns, if x is equal to, let's see, I shouldn't be running out of letters. Let me just write it like this. I'll say that if I consider a free P module is going to be of the form symmetric sequence, circle P. So X is just any symmetric sequence now. And if I take its lifted Boardman-Fock tensor product with respect to a free Q module, which is of the form Y tensor Q, just as though you have a free A modules of the form Y tensor A. If you take this tensor product, it turns out you have an exact description of it in terms of yet another monoidal structure on symmetric sequences. So it's actually going to be, again, a free module, like this. And this box product in arity n is given by the disjoint union over all L times m equals n. So instead of using the sum, you're using the product, you're using a different day convolution for people who like that language. XL, IM, and you tensor up. And the interesting thing about the tensoring up this time is that you're using sort of a matrix way of embedding sigma L cross sigma n in sigma n. Since n is equal to L times n, you actually look at these things matricially rather than straightforward. So you have this very explicit description of this lifted tensor product for free modules. Yes, thank you. Too many symbols. Yes, because it's a free P tensor Q module. Thank you very much. OK. Right, so what do you care about this? Oh, and there's one other way in which this tensor product is important, which is that if you take this lifted Boardman-Fock tensor product with a fixed Q module, it actually has a right adjoint. So this is the last thing I want to recall, which is that if I take any y, which is a Q module, there's actually an adjunction given by, well, on the one hand, your left adjoint is going to be tensoring with y from P modules. And tensoring with y is taking you into P tensor Q modules. And it turns out that there's a sort of a Hom functor, which I won't specify more than to say it's a right adjoint to tensoring with y. So knowing that there's this right adjoint is very helpful. OK, so homotopy theory. There hasn't been any homotopy theory so far, and this is a homotopy theory conference. So let me just say a few words about how homotopy theory comes into play in this operatic context. So I'm going to formulate this as a proposition, most of which, in the form that I'm giving it, is due to Benoît Fraisse. His book on modules over operads is a great place to find this sort of stuff. And also, part of this proposition was proved in the course of a work with Ben and Bill. So if I choose any operad P, there is a model category structure. And again, this is good. I'm going to stay in the context of simplicial sets and topological spaces, even though a lot of this, what I'm going to say here, actually holds in a more general context. So there's a model structure, on the category of right P modules, so that the following conditions are satisfied. So such that, for example, if I have a morphism of operads, this adjunction between pushing forward and pulling back is equivalent pair. So it's homotopically meaningful. And when is it equivalent equivalence? Well, it turns out that it's enough for phi, your morphism of operads, to be a weak equivalence in each level, as long as your objects are cofibrant in each level. So, and we know that this is equivalent equivalence if in every arity n, the map from Pn to Qn is a weak equivalence of cofibrant objects. So cofibrant in the model structure on sigma n spaces that you get by having the weak equivalences and the fibrations just defined and created in the underlying category. Okay, and the last thing is that if Y in mod Q is cofibrant in this model structure, then this adjunction here is a equivalent pair. And that really is one of the crucial elements for our proof with. OK. And the last bit of homotopy theory I want to mention is this. So this work of Bohrmann and Vogt that was later generalized by Berger and Moerdijk and then lifted to modules by us. It says that in this context, you have a cofibrant replacement functor, which is called W. It's the Bohrmann-Vogt W construction. It's a natural construction that is an object-wise weak equivalence that you can also lift to modules, some sort of W tilde, an equivalence here, so that you're going to have that W and W tilde give you cofibrant replacements, as long as the objects that you start with are sigma n cofibrant. So these are natural cofibrant replacements. OK, so in the 3 minutes remaining, let me say how this applies to configuration spaces. So the application to configuration spaces. The key is the following. That if M is framed, then there's an equivalence between the framed embeddings of k-disjoint copies of Rm, where M is an M manifold, to the configuration space of k points in M, just by shrinking each copy of Rm to the origin. So you have this homotopy equivalence. So this tells us that if we work with these embedding spaces, we can recover information about configurations. So we're going to consider an operad we'll call EM, which is given by applying this W construction, because we want something to be cofibrant, to basically sort of a framed embedding version of the endomorphism operad of Rm. And for any M, we'll consider the module that's given by taking the W tilde of the associated Hom guy. Also in looking at these framed embeddings rather than just all maps. OK, so this one is now going to be a module over this one. And a big, very hard theorem by Fedorovitz and Vogt, from 2015 shows that it's what they call additivity result. We take the Bohrmann-Vogt tensor product of these guys. It's actually, sorry, it goes the other way, that there is an equivalence from EM plus N to this tensor product, equivalence of operads. And then what we proved is that there's a module version of this, which says that, let me call this phi mn, that there's a natural equivalence from H m cross n to the pullback along this guy of hm lifted tensor hn. How does this tell us anything about configuration spaces? Well, we know that the kth level here is the space of configurations of k points in the product, which tells us then that this is going to be equivalent to what you get in arity k when you look at the lifted tensor product of these modules. This is the formula. It's admittedly somewhat complicated. On the other hand, this cofibrant replacement is something that's built up with very nice simplicial things that are built with free modules at the various levels. There should be a way, Ben and I haven't done it yet, and maybe we're not the right people to do it, to use this sort of description to actually do computations. And another thing that we would like to do is to say, once we have this, then we can use some of the knowledge one has of the embedding calculus, the fact that the space of embeddings of one manifold into another under good codimension conditions is given by derived mapping spaces of right modules, that maybe we can use this description to enable us to think about embeddings of products of manifolds into given manifolds. Thank you very much for your attention. Well, the idea was that this should be, what we wanted was a factorization homology type result that would give us this last theorem. Because this was about modules over a product, we thought that maybe we could use the fact that it was true in this Budowitz-Vogt case, which is sort of like the base case with looking at Euclidean pieces, that you could then use factorization homology to go from knowing what happens on elements of your atlas to knowing something about the whole module. But it turns out not to be necessary because these right modules actually have a fairly simple description, so that it's not hard to make covibrant replacement. Everything plays out really nicely without having to use the full power of factorization homology. The point is really, Budowitz and Vogt tell us what's happening on the Euclidean pieces, and then it turns out you can actually glue it all together in some sort of homotopy colimit in a way that's nice enough that it all just sort of falls out, once you know this homotopy theoretic results. No. No, they were really, really using the fact that we're talking about manifolds with a framing to be able to say something about this equivalence here. Another thing we'd like to do is to talk about more general G structures, more general framings for different subgroups of GLNR, but there's some issues about equivariance there that are not easy to figure out, and we're still working on that. So I think it can probably be done in any Cartesian model category, any Cartesian monodal category. I think that that's probably the case. There are some tricky things one needs to know. At some points, one actually uses the co-multiplicative structure without really realizing once we're working with Cartesian things. And then when you sit down to write things down with an ordinary tensor product, you say, oops, I need a coalgebra structure. So, yeah. None. None at all. M and N or any. It's just when we start talking about embeddings of products, if we were talking about embeddings of M prime cross M double prime into N, then we would need to know that the sum of the dimensions of M prime and M double prime was at most the dimension of N minus 3. So in that case, we could use these embedding calculus results and then perhaps come up with some sort of change of rings type spectral sequence to be able to say something about embeddings of a product into a manifold.